Can you form this alcohol from this aldehyde? What reagent do you need? Were you able to catch up?
Wouldn't it be, does this involve organometallics?
What else could it involve? How do we answer that question? Does it involve an organometallic? What conversion do you see? What functional group change do you see?
Carbonyl to an alcohol.
Carbonyl to an alcohol. And we have other reactions that do that, or is that strictly an organometallic transformation? We do have other reactions. What other reaction would take a carbonyl to an alcohol?
Reduction.
Okay, so reduction can take carbonyls to alcohols. Can we be descriptive in the transformation more? What substitution of carbonyl to what substitution of alcohol?
Going from a secondary to a tertiary, right? A secondary carbonyl to a tertiary alcohol.
Right? Secondary carbonyl to tertiary alcohol? Not right.
No. I'm getting a little confused.
That's okay.
I'm like, I'm still looking.
We gotta work it out. Primary to secondary. We base the substitution on the carbon and its bonds to carbon. So aldehyde attached to one carbon, primary. Alcohol with the carbon attached to two carbons, secondary. Does reduction change the degree of substitution?
No.
Reduction took our primary carbonyls and made them primary alcohols. Took our secondary ketone and made it a secondary alcohol. Took our our methyl carbonyls and made it a methyl alcohol. So reduction here sees the same type of transformation, carbonyl to alcohol, but reduction does not see this change in substitution. So organometallics are useful in that way. Organometallics add a carbon-carbon bond. That will increase the degree of substitution at your carbon. Did we form a carbon-carbon bond in this reaction? We sure did. One of the carbons in the newly formed carbon-carbon bond must have been a nucleophile, one must have been an electrophile. So here is an electrophilic carbon, and that is obviously part of the new carbon-carbon bond that's forming. And if I want to figure out what my other reagent needed to be, I need to figure out what that other carbon is that's bonding. That looks like this carbon, which must have been the nucleophilic carbon. So my reagent definitely needs an aromatic ring. somehow I've got to get all of those carbons into the new product. And I want this carbon on the right, the carbon of the aromatic ring, to be the nucleophile. Because I know the carbonyl carbon is partial positive, and that's part of the new carbon-carbon bond. So I need this carbon to be partial negative to make that carbon-carbon bond. How do I make a carbon negative? Bond it to a metal. So good answers here would be lithium or a magnesium halide bonded to the aromatic ring. And that would be just step 1. Step 2 would be what? Aqueous workup. Protonate the alkoxide that forms. Yesterday, our example of acyl addition, which is what we see here again. Yesterday, our example of acyl addition formed a tertiary alcohol, because that was the only way for us to form a tertiary alcohol from a carbonyl. Now what we're seeing is that you do not need to form a tertiary alcohol. Acyl addition just increases your degree of substitution when it makes the alcohol. So a little bit of practice then for you guys. Fill in the missing reagents. Oh, I wanted to make a quick, before you fill in these reagents, acyl addition, which again is carbonyl going to an alcohol of some type. That's a good way of looking at acyl addition. Works great with organolithiums and organomagnesium halides, the Grignards. You can think of those reagents as interchangeable. If, for example, you had given me this phenyllithium, but then on an answer key I show you phenylmagnesium chloride, those are interchangeable. On paper, they do exactly the same thing. In lab, maybe not. But on paper, these are interchangeable, and they work great for acyl addition. But it won't run with our cuprates, our lithium diorgano cuprates. We'll talk in a minute about what the cuprates are good for, if not for this. And we'll actually see the cuprates again later in the semester. Okay, but for now, can you give a starting material? Can you give a product? Can you figure out the reagent? fast work. Nailed it. I think the only thing here is it's the lithium bonded to this carbon at the bottom. Is it 1, 2, 3, 4, 5 carbons bonded to lithium? Or is the lithium there at the bottom?
The lithium is there.
You see how it looks like an extra one? Good. Great work.
All right.
Yeah, isn't it a crazy way to draw a molecule though?
Yeah.
It looks silly,
Yeah.
but it is right. Mm-hmm.
Okay.
Jaylee, did you do these in your OChem 1 class?
Oh, yeah.
Yeah,
Yeah.
okay. That came really quick to you.
All the like oxygen ones and like epoxides and all that we did in my outcome one.
Okay, so hopefully this unit feels like a good review for you then. Fingers crossed. Jaylee, if you want to help other people brainstorm, you're the second most expert in the room today. Maybe first most. I shouldn't assume anything. This works great. Is it 5 carbons?
Wait. 1, 2, 3. Isn't that? Oh, I see. Sorry.
No, that's okay. Yeah, I agree.
Counting's hard sometimes.
Mm-hmm. I hear you. The next one we're going to go over is this. Those are retrosynthesis arrows, meaning this which came from what it's pointing at, rather than this which goes to what it's pointing at. How you feeling?
Like that.
That's it, right there. But isn't it a funny little way to draw a molecule?
It is.
I don't know how to do that one.
Count your carbons. Do what you did here. Somehow,
Why is this? I don't get that.
it's a carbon bonded to lithium.
Yeah, but it's still bonded. Does that affect things?
It actually doesn't.
Okay.
Isn't that crazy? Like this. Isn't that a double bonded carbon? That's an sp2 carbon.
Oh.
It is one of those strange examples where nothing can stop it unless you've got an alcohol in the molecule or in the system. But otherwise, it can be any sort of carbon.
So that will go to an alcohol.
Mm-hmm.
But then, does it go this way?
You could draw it either way because really it's in and out.
Or is it off this carbon?
Oh, sorry. Which carbon did you say?
Oh wait, well it would have to be this carbon, right?
Yeah.
Okay.
That's the trend we're seeing is the carbonyl carbon becomes an alcohol carbon. Is that 4? There's 4.
There we go.
Okay. How'd you do up above?
I'm not fully confident in that one.
Okay. How many carbons in this structure?
2.
And how many carbons added to the molecule?
1.
And then how many carbons in the product?
2.
Oh, shoot. So how many carbons do I need if I'm going to add 1 to get to 2?
Just 1 carbon?
Mm-hmm. And then what does that look like? Yeah.
Oh, okay.
Yeah. Although what you're doing is showing one of the hydrogens, but not showing the other.
Okay.
So you could show it.
Show both.
Exactly. Or you could show neither. It's a weird one to show neither of. Do you know this one already? The 3 ways you can make it. Great. All right, so with this first one, what you guys recognized was I'm adding 1 carbon and I'm getting to 2 carbons. By the way, here's the CH3 that I just added, which means that this must have been the carbonyl carbon. And the carbonyl carbon already had 2 hydrogens off of it, and I added this 1 new carbon group, which means my carbonyl carbon was formaldehyde. Formaldehyde is the carbonyl precursor to get us to a primary alcohol. Regular aldehydes take us to a secondary alcohol, and ketones take us to a tertiary alcohol. Other ways that you could draw this, CH2O is another common abbreviation for formaldehyde. It's not wrong for those of you that even drew it just like this, just a double bond to O. That is technically following all of our bond line rules. Just looks funny. Okay, up above, the carbonyl carbon becomes an alcohol, and it gains a new bond to a carbon, and that carbon that it bonded to is an sp2 carbon. It helps to map your carbons here. I like to map through the nucleophilic carbon. For instance, here's my nucleophile, and it's going to attack something. Here's my nucleophile. Here's what it attacked. Carbon 2. So I need to add a bond to carbon 2. Everything else stays the same. Here's my nucleophile. Carbon 2 attacks carbon 3. And so I get my new system. I just like to count through the nucleophilic attack because in my head, that's how it happens. The nucleophile is what comes in and shares the electrons to make the bond. I like to count a little bit behind the nucleophilic carbon when I can, so that I can count up to it and kind of get this longer chain and make sure that I have all of my atoms in the right spot. Here, I think I might do it the opposite way. I've got this 6-atom chain, and in my product, my carbonyl carbon turns into an alcohol. An aldehyde becomes a secondary alcohol, acyl addition with a Grignard. So I'm looking for 7, 8, 9, and 10 to come in. So here's 7, 8, 9, and 10. But it's not enough to just add those 4 carbons. I need my nucleophilic carbon. So I could have added lithium. I could have added magnesium bromide, magnesium chloride. But N-bule is actually a really commonly formed compound. So this is one that would be easy to make, easy to get, easy to use. Now, in these retrosynthesis problems, I have a tertiary alcohol, and I want to figure out what are all the ways that I could make this tertiary alcohol. First, recognize that the alcohol carbon was a carbonyl carbon. And I've got 3 distinct groups bonded to that carbonyl carbon. So I have 3 distinct pathways that could get me to that alcohol. So I'd like you guys to find those 3 ways. Do you want me to give you one first? What if I made this alcohol by acyl addition with the methyl group? Don't like that it was in that color. My alcohol carbon shows as a carbonyl carbon, and I give it the methyl group with an aqueous workup. The methyl group would add to the carbonyl carbon. Ketone becomes a tertiary alcohol, and I have my product. Now can you find the other two? Morning. This one, would you say that's about the same as this? Just abbreviating the ring as pH? Okay. Because it might need to think about the carbon count then.
Yeah, because I need to get rid of that one right there.
What's the substitution of our alcohol?
Tertiary.
So all of the carbonyls that precede it have to be ketones. But this looks like an aldehyde.
So they all have to be. So could I technically do something like that instead?
Well, it'd have to be, because if you're trying to add this group, that means that
Oh, yeah.
that group stays there.
Yeah, I'm missing a carbon.
I think you are missing a carbon, yep. In fact, that is my intended shortfall here. I'm expecting that you guys might miss carbons. So map them, map your carbons to see that you've got them all. This one's missing a carbon. The way that you've drawn it, would you say it's essentially what's up there? Benzene bonded to lithium, phenyl bonded to lithium.
Oh, true, this is a carbon.
So lithium to carbon
Mm-hmm.
to the benzene.
Yeah.
Because it looks like a covalent bond between lithium and pH. I think what you need is a vertex that has an implied CH2. Perfect. And then this one is also missing a carbon in that similar way. And maybe it's that same idea. Yep. Yep. Great. So we're still missing a carbon because 1, 2, 3.
Oh, yeah, so I just need to add one more right here.
Yep.
Oh, okay, there we go.
Perfect. And now you see how that actually fixes the mapping that you had at your carbonyl. At one side, your carbonyl was 2. At the other side, your carbonyl was 3. Now, what's our substitution of the alcohol?
It's tertiary.
Which means that all of the carbonyls will have to be ketones. But this looks like an aldehyde. So you're adding this group, which means you keep this group and you keep the methyl.
Okay. So there would still there be one right there?
Here's how I would say it. You've mapped your structure so it goes 1 through 6. At 3, you have both a methyl, an alcohol, and then 4, 5, 6. But then in your starting material, you've got 3. The alcohol is going to come from the carbonyl, no methyl, 4, 5, 6.
Okay.
Are you adding both the 1 and 2 group and the methyl in this step? I know it's confusing with this arrow because you're starting from the right to move to the alcohol on the left, but we're drawing the arrow as we're not going to the right, we're going from the right.
And then go into the
But as you go this way, are you adding both the methyl and that benzyl group? No. Great. Great. Okay, I think you guys got it. I can just pick any of my 3 groups coming off of this chain. I leave the other 3 groups attached. Sorry, I leave the other 2 groups attached. So in this case, I left the benzyl and the allyl side attached. I added the methyl group. This way, I'll add the phenyl group. Now it's important to recognize it's not just benzene attacking. Like these could have been written as PHLI or PHMgCl, but it's not the benzene ring that bonds to the carbonyl carbon. It's the benzylic carbon that bonds to it. 1, 2, 3 is carbonyl. 1, 2, 3 is carbonyl. And now in this case, the carbonyl is still a ketone, needs to still have the methyl group and the allyl group, methyl and allyl. And this last one, I'll keep the benzyl and the methyl group. And I'll add the allyl group. Once again, it's important to realize how many carbons you need. 1, 2, 3 off of the carbonyl. 1, 2, 3 off of the carbonyl. So mapping your carbons can be life-saving in figuring out how many carbons you need. This one's a challenging one because if I map it once, I gotta map it in a bunch of different directions. Although I guess this seemed to come pretty naturally to you guys, so I will demonstrate just mapping across. Here, I keep 3, 4, 5, 6, and I'm adding 1 and 2. 2 is my nucleophilic carbon attached to 3. 3 has a methyl group. 3 has a methyl group. Down here, I'm adding 4, 5, and 6. 4 bonds to 3. 3 has a methyl group. All right. Good work. Let's talk about some other things that organometallics can do. So they can do acyl addition, carbonyl to alcohol. They can run NAS, and this is on your worksheet where it demonstrates the NAS reaction. We know that NAS requires having a leaving group halogen, and we know that it's sped up by having electron withdrawing groups, ortho or para to the halogen. And we know that the nucleophile substituting the halogen has to be a strong nucleophile. Well, organometallics are strong nucleophiles. So if I introduced here my phenyl Grignard, like what you guys are using in lab, benzene acts as a nucleophile because of the Grignard and substitutes the bromine. Maybe a challenging one because it ends with a para-nitro biphenyl, which is a biphenyl in general is just kind of a confusing structure to draw. But let's do a few more examples. Whoa. Oh, also notice that we don't need a workup. Esmeralda, how are you doing on all of this? You got it?
Yeah.
Okay. Oh, I'm sorry I don't have these made as a worksheet. This is why I went to worksheets, because now you have to put in the work just to copy it down before you can even solve it. It is. Yeah, it's pretty strange if you ask me. It is quieter. Why, though?
Sorry, part of it's down here.
This will not work as a starting material. No, 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 no.
Not just that.
Not just benzene. Oh, well, you've made a 5-bonded carbon. What does NAS require?
I can't even remember, to be honest.
Nucleophilic aromatic substitution. So the nucleophile has to attack the carbon, and a leaving group has to leave. Without a leaving group, nothing will happen. This is good. Mm-hmm. Mm-hmm. Yep. Good. Great work. Mm-hmm. Great.
So we need that halide to do NAS.
Correct.
Okay.
Correct. If I gave this on an exam, this blank, with this reagent and this product, and I wanted you to fill in the answer, do you think that I would accept this answer? Why not? Do you think I should accept this answer? Regardless of whether you think I would accept it or not, do you think I should accept this answer?
I think no, because then students could just be taking a wild guess with the X.
Take a wild guess, so I shouldn't. Yes, because
It doesn't matter what it is.
it doesn't matter what it is, so long as it is a halide, which is what we use X for. I don't like it. Because if you know that it needs to be a halide, then just pick a halide. And I'd actually rather see that you know it should be a halide, because I have students that make it through the end of OCHEM 2 and go, oh, X means halide? So maybe they just guessed. Maybe they didn't know. I agree. This isn't a molecule, though. This is a generic form of a molecule, right? The molecule would be having chlorine there, or having bromine, even having fluorine or iodine, but I think you guys have caught on to the point now that we work mostly with bromine and chlorine. All right, now you guys have been showing me organolithiums and organometallics. I'm going to show you that we can solve this one up here with diorganocuprates. Because we said that diorganocuprates would not work for acyl addition, but diorganocuprates, organolithiums, and organomagnesium halides all work for NAS. And for the next one we're going to look at, which is SN2. So if you had given me, for this product up here, if you'd given me that vinyl lithium or vinyl Grignard, those would have worked just as well. Can anyone tell me why we're not doing an aqueous workup for this reaction, for these reactions? No oxygen that needs to be protonated. Nucleophile attacks carbon, breaks aromaticity. Negative charge goes into the most stable resonance forms, kicks off the leaving group. No aqueous workup necessary. All right, our last one up there. Obviously, is it obvious? Methyl group, not a leaving group. The methyl cannot get kicked off by a nucleophile. Nitro group, not a leaving group. NAS reactions, remember, substitute our aryl halides. So in this case, I substitute with a tert-butyl group because that is what my nucleophile is. It's a tert-butyl carbon. All right, the last way that we can utilize organometallics is by SN2 on primary alkyl halides. I lost my sheet, which is why I didn't give you guys the fill out of that diagram. Sorry, Justice, I'm just going to borrow this for a second. So on that sheet, I had given you guys just a generic organometallic, RM. And so generically, we could show all of these steps This is what your worksheet has for you. That NAS just needs an aryl halide. Acyl addition, hey, notice that the R product added to this alcohol carbon, which means that alcohol carbon must have been the carbonyl carbon, which already had a group that was shown attached to it. And that requires 2 steps. We need to show the aqueous workup. Then we can show the organometallic doing substitution wherever that new organo group bonds to, wherever that new carbon-carbon bond is, there must have been a leaving group on that carbon. Why do you suppose these need to happen on primary alkyl halides? Secondary alkyl halide is going to give competition for elimination. And a secondary alkyl halide being eliminated by a strong base, it has some favor for doing that elimination. So primary alkyl halide favors substitution and won't favor elimination. So we'll do a few more practice problems. Let's just wrap it up with these. At your, yeah, trippy. It's like all chrome, but it's not chrome, it's iridescent. That's a good word. Don't be fooled on that second one. Don't get fooled. Count your carbons, map them out. Yeah, you didn't get fooled, did you? Good work, Jane Lee. I'm sorry for putting aromatic rings in both of them. That was, I just like it. SN2 doesn't need the aromatic ring on it. I'm just running out of steam to think of questions. I'm going to give you guys some practice problems soon, I hope. Actually, I think we're going to do more worksheets. Okay, I did mess up and I didn't make copies of this next one, so let me ask this. Who relies on having the worksheet physical and who can use the one that's on Canvas? Anyone need the physical one? 3. Okay, I've got one more then. I'll make sure that the next worksheet is published though so that you guys can get at it. Because I didn't make copies or update it. It'll be good though, it's a good one. We're going through a hiring process in the department right now, and we got 1 week to score candidates by criteria on their application before we pick who to interview. 1 week to score 55 candidates, and they gave me the list of 55 the day before my wedding. So of course I'm not going to be scoring candidates during my wedding weekend. That's ridiculous. So I came back Tuesday with 55 candidates to rank in 3 days. Yeah, thank you. It was really fun. So I feel bad. This is the least prepared I've felt in many a semester because I am always updating this stuff, and having not updated these things because my mind is just on all the other things going on doesn't feel good. Don't like it.
You're doing great.
You're feeling great?
You're doing great.
Oh, thank you. You're too kind. Oh, that's not even what I want. Can you name the products? Actually, for the first... No, why don't you name the product for the first one, name the starting material for the second one. All right, the next one is posted on Canvas. Alcohols and epoxides synthesis. Let's see, did I get around to seeing everybody's answers too?
It's a sec butyl, right?
It's not a sec butyl.
It's a isobutyl.
It's an isobutyl. You
Okay.
got it. Where was your answer, by the way?
This one.
What's this? Yeah, okay, good.
And then this one I stuck on.
Got stuck. Count your carbons. Recognize what category we're doing it in. Good, great. Lost a carbon in there. So here's a nucleophile. 1, a taxoelectrophile. 2, 3, 4, methyl group off 3. 1, 2, 3. Methyl group off 2.
Like that? Or is it technically gonna be?
Sorry, I just can't see anything until you're done. It's that.
Okay.
Perfect. And this is not, this has no leaving group. Ah, so you went from methylbenzene to chlorobenzene.
Yeah.
But that
But
actually
that's also incorrect, 'cause
steals,
then
that steals a carbon.
there's that.
There you go, chloromethylbenzene. Yep. Let me know if you can't find it, Evan, okay?
I just barely got to.
But you're doing great. Yeah, absolutely. Great, great.
I cannot find it.
Under unit 3. Dang. Because it's showing as published for me.
This one?
Yep, it's showing up on hers. So it might be just a refreshing Canvas issue. All right, here's my nucleophile, attacks my electrophile, 3, 4. And I've got my nucleophile, attacks my electrophile, 3, 4. I've got a methyl group off of 3, a methyl group off of 3. I saw that some of you guys also drew this like that. Perfect. Isobutyl benzene. Or you could actually call it 2-methylpropylbenzene. You just have to put all of that into parentheses, because otherwise someone's going to get confused and think that you meant 2-methyl-1-propylbenzene, that you had a di-substituted benzene ring. And you want to tell them, no, the methyl is a substituent of propyl, 2-methylpropylbenzene. Now here, I've got 2 carbons. This, I was not trying to trick you so much as expose you to the different ways that we can draw these reagents. So here's my nucleophilic carbon, 1, 2, attacks 3, and then 4 is the ring, which means in this case I need 3 to have a leaving group. So chloromethylbenzene or bromomethylbenzene. And I think once again you would want to put these in parentheses so that somebody doesn't think, oh, they forgot to tell me if the bromo and methyl are ortho, para, or meta to each other. They didn't tell me whether it's ortho bromomethylbenzene, meta bromomethylbenzene, para bromomethylbenzene. It's not. It's bromomethylbenzene. You could also name these not based on the aromatic ring. You could name them as a carbon chain, in which case the product here would be, let's see, 2-methyl, 1-phenyl propane, because my shortest carbon chain would start here with phenyl and have methyl on 2. And this could be named bromophenyl methane, although that I don't like as much because it almost gives the impression that it's a bromophenyl group, like the phenyl group has bromine on it. Who said language made anything more clear? Am I right? All right, we are going to transition now from reactions that form alcohols to reactions that start with alcohols. You found it?
Yeah, I had to log in through Safari. It was really weird.
Oh, that is weird. Okay, anybody else want my last sheet? You're good? Okay. Now, this chapter in our textbook or I kind of forget if it's 2 chapters because I just think of it as one. It sometimes includes sulfides. I don't teach on the sulfides often, but it covers alcohols and ethers and epoxides. You guys might remember hearing me say during our OChem 1 review that water is often a precursor to making an alcohol. When we had our alkene addition reactions, an alkene addition that included water included an alcohol, or formed an alcohol, whereas a reaction that included an alcohol formed an ether. So water is a precursor to alcohols. Alcohols are precursors to ethers. So in this unit where we see reactions with alcohols, we are looking at most all of the reactions that form ethers. They go hand in hand. In fact, I'm trying to think, and I don't believe that there is a reaction that forms ethers that isn't a reaction with alcohols. So that's where we're going now. We've just looked at preparation of alcohols. We took a little detour to talk about other things organometallics can do. Now we're going to look at reactions with alcohols. All right, we'll start by filling out this this big diagram. I've learned my lesson not to make them this big, but again, I didn't have time to change this. We've got 7 arrows on here. And I'm going to do my best to kind of name these, but also spread them out and show what the reagents necessary are. All right, first, we know that alcohols can go through elimination. Acid catalyzed dehydration. It's an E1 elimination, so it forms the most stable alkene possible. Alcohols can also go through substitution, like with HBr or HCl. And it's important to remember this is SN1. What's the stereochemical significance of being SN1? There's a carbocation intermediate. But what's the stereochemical implication there? Rearrangements. And loss of configuration, R or S, can't be conserved. Then we have substitution to an alkyl halide, but with these inorganic reagents instead of with acids. And this is SN2. And the stereochemical significance of SN2 conserves configuration, or sorry, flips configuration, inverts configuration, no carbocation intermediate, no chance of rearrangement. Another thing that we saw alcohols can do is what I call transformation. We can transform the alcohol into a good leaving group. Some places you look will call this a pseudo-halide because the alcohol oxygen no longer behaves like an alcohol. The alcohol oxygen now behaves more similar to the halides in that it's a good leaving group. I do want to take an aside to look at this reaction right now because we understand a lot more of it now that we've gone through our aromatic chapter. So this compound is called tosyl chloride. And although I haven't shown you how to make tosyl chloride specifically, we have looked at how to make sulfonic acids, like toluene sulfonic acid is a synthesis we could run. And what happens with the alcohol starts with a type of carbonyl type addition. Oh, I really screwed that up. Our alcohol adds to the sulfonyl group, and it creates this intermediate, which is not a very stable intermediate, and this intermediate just kicks off the chlorine, and that chlorine then comes in to act as a base and take off the hydrogen from the alcohol. What we end up with eventually is a sulfonyl ester, where our original oxygen is now bonded to that sulfonyl group. We're substituting the chlorine. So it's a type of substitution reaction. It's not really SN1, it's not really SN2, it's not really acyl substitution, it's sulfonyl substitution. But now that we have an oxygen connected to that sulfonyl group, it is a lot easier to break this carbon-oxygen bond. That oxygen will take the negative charge and delocalize it in resonance with both of the other oxygens. Typically, when an oxygen leaves, for instance, if we tried to imagine the carbon-oxygen bond of the alcohol leaving, it creates a strong nucleophile. So to create a positive charge in the presence of that negative charge, it would just recombine. Here, that negative charge is not really a negative charge. It's a negative 1/3 charge distributed across all oxygens. So it means that oxygen can leave and not be such an aggressive nucleophile to recombine. It leaves and it stays off of the carbon. Bad leaving group, all I've really done is swapped out the hydrogen for this sulfonyl group, and now it's a good leaving group, a pseudo halide. Good stuff? One of the other reactions that we saw from OChem 1 with alcohols was the halo-ether addition reaction. So we take an alcohol, we take an alkene, screwed up on drawing my alkene. I'm just going to show us ethylene, so a small alkene. And we take a halogen like bromine. Across the two carbons of my alkene, bromine added on one position and the alcohol added on the other. What functional group did we end up with in the product? An ether, because alcohols are precursors to ethers. I do believe that is all of the old reactions with alcohols that we saw. So these last two are new reactions with alcohols. first, a very strange thing. Alcohols can serve in place of water in our alkene addition, acid catalyzed hydration reactions. So if I take this alkene and I treat it with acid in the presence of my alcohol, first of all, we know how the alkene behaves in acid. The alkene behaves as a base. The alkene donates electrons to hydrogen and forms a carbocation. Where does it form the carbocation? On the most substituted carbon. And that most substituted carbon in this molecule has the potential to rearrange. That carbocation in acid-catalyzed hydration is then attacked by water. But what is water if not inorganic alcohol? So by substituting water with alcohol, we form an ether. Now, I get that that is a very strange looking ether, but aren't all ethers a little strange looking? You can see the original sec-butyl chain of the alcohol, and you can see the original methyl-butyl chain, or isobutyl, if you will. Oh, it's isopentyl. Of the alkene. The alkene carbons actually both got hydrogens because of that carbocation rearrangement. And the alcohol acted as a nucleophile to that most substituted carbon. If we took this a step back, we can see how the alcohol and the carbocation come together. This is not necessarily a mechanism you need to know, but it's not a mechanism that you don't know. It's a mechanism I already tested you on. It's the alkene, it's the acid-catalyzed hydration mechanism. It just isn't hydration anymore, it's esterification. Form an ether. Oh, I'm sorry, I'm realizing I haven't named these yet. So this brown one was the halo ether. Brown. I'll be honest, I made up the name for this one, so tell me if it doesn't make sense. Acid catalyzed esterification. Can you even read it? I made it up. Aren't all words made up? Someone made up the word hydration at some point. Why can't I make up the word esterification? Forms an ether, right? I don't have a better name for it.
I like it.
Thank you. I've tried coming up with better names for it, but it just... another name for it would be like alcoholysis, reaction with an alcohol. Oh, I do remember the other one that I skipped over. So I think I'll do that one, a review that I skipped over. I'll do that one next. And then I have a few more new reactions to show. So for this last one, this is also SN1, SN2, but rather than SN1, SN2 on the alcohol, we're going to show SN1, SN2 with the alcohol. The example specifically that I'm showing here is, you tell me, is SN1 or SN2? What type of mechanism would sec-butyl alcohol and bromomethane go through? Take a few seconds to think about it. I'm going to get you to raise your hands to vote. Will this mechanism go SN1 or SN2? Raise your hand if you think sec-butyl alcohol and methyl bromide react by SN1. Raise your hand if you think sec-butyl alcohol and methyl bromide go by SN2. Brenna, what do you think?
What?
Do you want to justify?
Because it's adding on to the same place as alcohol?
The methyl is adding to the same place?
Yes.
Okay. Anybody from SN2 want to justify? Oh. So the majority doesn't have a strong gut feeling?
Because it's a methyl, and they go through SN2.
So I think, Brenna, your confusion was that the alcohol carbon isn't going through any change. So the methyl adds to where the alcohol is. Well, actually, the alcohol carbon hasn't changed it at all. Instead, it's the alkyl halide that either will form a carbocation, SN1, or will not form a carbocation, SN2. And a methyl halide, good at making a carbocation or not very good at making a carbocation? Why not? It's unsubstituted, so it has very little electron density, so it's a wide open positive charge. So it takes a lot of energy to get that to be a carbocation. It actually takes less energy for this weak nucleophile to even do SN2. So this mechanism would go by SN2, even though it's a weak nucleophile. Primary alkyl halide, probably SN2. Secondary and tertiary alkyl halide, SN1. In fact, we could make this, this ether that we saw down below, we could make that ether by an SN1 substitution rather than this new acid-catalyzed esterification. Still using this sec-butyl alcohol, I would just need to have a good leaving group on that tertiary carbon. Weak nucleophile, tertiary carbocation from the chlorine leaving, and then the nucleophile just adds on. Okay, a few new reactions. The Williamson ether synthesis is a reaction that you basically know already, but have not seen put together. And I find it so silly that textbooks will kind of masquerade this as a reaction that's new to you and just not introduce it earlier. The Williamson ether synthesis takes an alcohol and deprotonates it to turn it into an alkoxide, a strong base. Notice that the base we're using, sodium hydride, is a very strong base, which means the equilibrium completely deprotonates the alcohol. Then introduces an alkyl halide to the mix. After step 1, we just make an alkoxide. And then we introduce the alkyl halide, and this is what you already know from OChem 1. Take a strong base, strong nucleophile, like this alkyl halide, and watch as it substitutes by SN2. And I added on too many carbons in my product. And I figured out that I added on too many carbons because I mapped my carbons. Well, let's be honest, I mapped my atoms because I also mapped the oxygen. 1, 2, 3, oxygen makes 4. Oxygen attacks 5, that's where my leaving group is. 5, 6, 7. And then I have this 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I screwed up. You see how mapping can help you recognize? But do you see why I call it mapping? Because I've just got them numbered in one place. It's not like I'm doing nomenclature with it. So 5, 6 should have a methyl group coming off of it. 7 should be the end of my chain. 5, 6 with a methyl group. 7 is the end of my chain. So you already know Williamson ether synthesis. You just didn't know that the alkoxide was made from an alcohol using a strong base. Does that make sense? Williamson ether synthesis, essentially the epitome of SN2. All right, then we've got the acid-catalyzed esterification, and I didn't make this one up. So I feel like this makes a lot of sense. Acid-catalyzed esterification is also sometimes called the Fischer esterification, sometimes called Fischer-Smith esterification, but I actually hear it more often just referred to as Fischer because screw Smith. I don't know. That doesn't make any sense to me, how some people can think it's named after 2 people, other people think it's named after 1, and I think that it should just be named after what it does. If anyone renames that acid-catalyzed esterification as the flood reaction, I'll roll over in my grave, because I know it'll happen over my dead body. All right, well, obviously, we need to make an ester in this reaction. And as we know, we're starting with some alcohol starting material. And we know that there will be an acid catalyst, H+. So the question becomes, what is the starting material? If I can get to an ester using an alcohol, what functional group do I need to transform? Obviously, it should be some sort of carbonyl. I need a carbonyl to just get my alcohol in there. And not any carbonyl works. Our starting material for this is a carboxylic acid. Carboxylic acids react with alcohols in the presence of an acid catalyst to give us esters. We're going to look more at this reaction in a later unit. We're also going to look at trans esterification. Take one ester, react with a different alcohol, get a different ester. Kind of in the same vein here. But this is just where our textbook introduces esterification. We're going to look at the mechanism later in the semester as well. Okay, the last class here, and this one's a big one. And I don't know why, for whatever reason, I don't have this on the sheet. So this will have to just be something that you add in. It's going to look a bit like the reduction of carbonyls to alcohols. Slight distinction though. We're going to start with oxidation with a mild oxidizer, pyridinium chlorochromate, PCC. Something small, like methyl alcohol, gets oxidized into formaldehyde. So remember when reduction added hydrogens to my structure? Oxidation is removing hydrogens from my structure. Remember when reduction decreased my number of bonds to oxygen? Oxidation will increase the number of bonds to oxygen. So this has taken CH3OH and left us with CH2O. We've removed, of course, the hydrogen from oxygen, but we've also removed a hydrogen from carbon. All right, that's my smallest alcohol, and it gets transformed into my smallest carbonyl. When I take a primary alcohol and oxidize it, I get a primary carbonyl. Primary alcohol to a primary aldehyde. When I take my next most substituted alcohol, a secondary alcohol, my mild oxidizing agent transforms it into a ketone. Do you hear the vocabulary in these descriptors? Primary alcohol to aldehyde, secondary alcohol to ketone. Being able to describe your functional groups like that can go a long ways in understanding what transformations, what syntheses are possible. All right, now I want you to imagine that we take a tertiary alcohol. Let's say we take the tertiary alcohol that you guys are synthesizing in lab this week, and you try to oxidize it. We took a hydrogen off of methanol to make an aldehyde. We took a hydrogen off of our primary alcohol to make an aldehyde. We took a hydrogen off of our secondary alcohol to make a ketone. What hydrogen can I take off of my tertiary alcohol? None. The same way we cannot form a tertiary alcohol by reduction, I cannot oxidize a tertiary alcohol. Justice, what does NR stand for? No reaction. Methyl, primary, secondary, those react to oxidation. Tertiary, no reaction. Now let's see how each of these groups reacts to a strong oxidizer, chromic acid. Now there are a lot of different ways to write out chromic acid. You will see me consistently write it as chromium trioxide in sulfuric acid. What's funny is that this reaction will pump out carbon dioxide and water. But we need to understand how it gets to pumping out carbon dioxide. First, the chromic acid oxidizes the carbon once. It removes one hydrogen and makes the formaldehyde. That, by the way, is exactly what our mild oxidizing agent did, but our mild oxidizing agent stopped there. Chromic acid is a strong oxidizer, which means that chromic acid further oxidizes formaldehyde. It takes off a hydrogen and replaces it with a carboxylic acid. That is formic acid. Nasty stuff. I heard of a geologist that used formic acid once, got some on their leg and had an open wound for like 50 years because of formic acid festering in his body. Nasty, nasty stuff. Formic acid has been oxidized twice from formaldehyde. But formic acid can also be oxidized by our strong oxidizing agent, because this last hydrogen from methanol can be oxidized into a carboxylic acid. And do you know what this reagent is? This chemical? It's in your blood, it's in your soda, it's in your champagne, it's in your beer, it's in the oceans. Carbonic acid. And carbonic acid is not very stable as itself, which is why when you shake your soda, a bunch of carbon dioxide comes out, because as you form that carbonic acid, it decomposes. And it decomposes into carbon dioxide and water. So if, for example, you wanted to know, is it useful in any way to take methanol and oxidize it with a strong oxidizing agent? The answer is not, unless you want to make carbon dioxide and water. Methanol with a mild oxidizing agent, a lot easier. Or I should say, a lot more useful. All right, well, that's an interesting one. But the rest of them are not quite as interesting. Actually, let me show you some other ways that chromic acid can be written out. It can be written as sodium chromate in sulfuric acid. A primary alcohol gets oxidized to a carboxylic acid. Once again, chromic acid is really good at doing what pyridinium chlorochromate does, and then going further. Just like how formaldehyde got oxidized into formic acid and formic acid into carbonic acid, a primary alcohol gets oxidized into an aldehyde, and that aldehyde gets oxidized even further. Another way that you might see chromic acid written out is in the form of potassium dichromate. But notice how sulfuric acid is written with each of these, because it's that sulfuric acid that actually makes chromic acid chromic acid. Chromic acid did nothing different to that secondary alcohol. Our mild oxidizing agent could only oxidize one hydrogen. That was it. It oxidized 1 hydrogen from methanol, 1 hydrogen from primary alcohol, 1 hydrogen from secondary alcohol. Our strong oxidizing agent can oxidize all 3 hydrogens from methanol, both hydrogens from our primary alcohol, but still only has 1 hydrogen to remove from our secondary alcohol. Okay, I think this is a good place for us to wrap up, but there is one last oxidation. So if you guys can remind me, we can start off here. I might have time to just get it to you. We have a selective oxidizer. It's a radical oxidizer. Manganese dioxide, MnO2. Oops. It leverages resonance stabilization to oxidize benzylic and allylic alcohols. You should notice that aryl alcohols can never be oxidized. Oh, that's not true. We just aren't going to. There's no hydrogen there either for them to be oxidized. It doesn't oxidize anything that is too far away from the ring. It has a radical intermediate, and that radical is stabilized by the pi system. In fact, this same thing happens with our allylic alcohols. Things that are not allylic do not oxidize. Things that are allylic or benzylic can form aldehydes or ketones. Would you say that MnO2, which is a selective oxidizer because it only oxidizes benzylic and allylic alcohols, would you say that MnO2 is a mild oxidizer like PCC or a strong oxidizer like chromic acid? Why? What makes you say mild? That is what I would say makes it selective, is that it will only do benzylic or allylic, but it can still do them. So does it behave more like a mild oxidizer, PCC, or a strong oxidizer, chromic acid? What's the difference between our mild and our strong oxidizers? Ketones, not different. But primary alcohols, different. A mild oxidizer takes an aldehyde, forms an aldehyde. Strong oxidizer forms a carboxylic acid. And what does our selective oxidizer do? Only forms aldehydes or ketones. This makes it more mild. It's not going to oxidize an aldehyde like our strong oxidizer does. It's both selective and mild. Okay, thank you guys. Thank you for your time. You have the weekend to work on practice problems and your homework. Try and dig into some synthesis too. And next week, we have the entire week to look at reactions with ethers and reactions with epoxides and do synthesis. I think we're going to have a lot of time for synthesis next week. So be prepared. I'm going to have some activities for us. Okay. Enjoy your weekend.